my pleasure to introduce our speaker today for the annual SID William Montagna Lecture. As most of you know, the William Montagna Lecture is given annually at the Society's annual meeting, intended to honor and reward and really recognize the Society's young, active investigators. The primary emphasis for the award is given to researchers in skin biology, and this year we have the honor to welcome Dr. Valerie Horsley here from Yale University. She obviously needs no introduction, but I'm going to give you one anyway. She began her scientific training as an undergraduate at Furman University and was awarded a PhD from Emory University. And after completing a Damon-Runyon Cancer Research Foundation postdoctoral fellowship in Dr. Elaine Fuchs's laboratory at the Rockefeller, Valerie started her independent laboratory at Yale University in the Department of Molecular, Cellular, and Developmental Biology. Her lab focuses on using the mouse as a genetic tool to understand a lot of the players in the dermis and how that contributes to stem cell biology, cellular differentiation, regeneration, and disease. Since 2011, she has been the Maxine Singer Associate Professor in Molecular, Cellular, and Developmental Biology at Yale. Her list of awards is too numerous to list, but I will highlight a few. She's won the Pew Scholar Award, the Presidential Early Career Award for Scientists and Engineers, and is currently the Rosalind Franklin Young Investigator. So please welcome Dr. Horsley to the podium to deliver the William Montagna Lecture.
Thank you, Kevin, and thank you to the Society for continually supporting junior and young scientists. It's really been a welcoming environment for me to grow up as a skin biologist, so I really appreciate it. And so today I would like to give you some background and tell you some of our unpublished work on how we're learning about the cells in the skin and how they in the dermis and how they regulate tissue regeneration and skin biology. So this is all of our favorite organ, the skin. It's so great to see thousands of people here that are all in love with the same tissue as me. And we are really appreciative of the epithelial cells that create this essential barrier, as well as the supportive cells in the dermis. And the majority of the field studies those epithelial cells and how they're regulated. And if you look at the papers in PubMed over the last 15 to 20 years, you can see if you just search for epidermis, there's about twice as many papers that reference the epidermis versus the dermis. Yet there's so many cells in the dermis that can regulate this epidermal compartment. And so we've really been trying to focus on how the epidermis is regulated by stromal cells in the dermis. And so in my laboratory, we think about the epithelium as this sheet that is tightly adherent and is sitting on top of a rich dermis that's on extracellular matrix proteins that are secreted by the fibroblasts. There are neural innovations that allow us to sense our environment, immune cells that act as our first barrier, first response to external pathogens. And in my laboratory, we've been thinking a lot about the different cells of the mesenchymal lineage, in particular, these lipid-filled adipocytes that exist. I don't know if I can do that, that exist within the stroma. And so we know adipocytes are lipid-filled mesenchymal cells that exist and grow and are specified to specific locations within the human body. In the adipose field, primarily these have been focused on in the visceral or subcutaneous depots because these have been implicated in metabolic and diabetic disorders. However, we know that there are other depots where adipocytes are found, including the bone marrow, and these have been thought to regulate hematopoietic stem cells. In the mammary gland, adipocytes surround the mammary epithelium, and we've become interested in the adipocytes that also exist within the skin. And if you look at sections of skin from both rodents and human tissue, you can see that the adipocyte layer is quite a large portion of the skin tissue. you can see that surrounding the hair follicle is this white region that's full of lipid-filled adipocytes. And in human skin, underneath this fibroblast-rich dermis, also surrounding hair follicles, is this thick adipose layer. And we really don't know very much about what it's doing there and how it's regulated. A recent paper used MRI to kind of characterize the adipocyte layer in the dermis. And you might have learned that this layer was called the hypodermis. And we believe that the hair follicle can only reside within the dermis. And so we have tried to rename this depot to dermal white adipose tissue. It's quite distinct from the subcutaneous depot and is contained throughout the skin. So you can see that by this MRI imaging technique and how large dermal white adipose tissue really is. On the left, you can see in green a projection of the dermal white adipose tissue as quantified by MRI. And then on the right was a study looking at different human subjects, patients, and looking at the thickness of the dermal white adipose tissue. And it was estimated from this paper that dermal white adipose tissue can be up to 2 to 17 kilograms. And visceral fat, which we think where we store most of our fat in our belly, is about 15 kilograms. And so this really can be a large part of where we store fat in our body. And in particular, this has been implicated in some human disease. Here's a paper that was recently published from Japan where this young boy had alopecia on his scalp, and it associated with this area of alopecia was a lipodystrophy, as you can see by MRI, in his scalp region. In addition, we know that plastic surgeons often isolate fat and inject them into wounds, and this is thought to help reduce scarring and promote wound healing. And so in my laboratory, we've really wanted to understand what are these adipocytes doing in the skin tissue. So does this regulate tissue regeneration? We know that adipose tissue stores fat in the form of triglycerides, and these can be broken down through a lipolytic pathway to release lipids that can provide energy for different tissues in our body. We also know that adipocytes can secrete proteins like leptin, which are called adipokines, and these can signal to various cell types to regulate tissue biology. We initially were interested in this because of the dynamic changes that occur in dermal white adipose tissue associated with the hair follicle cycle. It was noted in the early 1900s that the adipose tissue in rodent skin expands almost twofold in size going from the rest stage of the hair follicle cycle to the growth stage. And so we were curious whether this was just filling of lipid or also a combination of stem cells within the adipocyte lineage that could form new mature adipocytes. And so we analyzed by flow cytometry different mesenchymal populations, which we can isolate from skin tissue. And using a panel of different cell surface proteins, we identified a population of cells that we've termed these adipocyte precursor cells that in mice express CD34, CD29, and SCA1. And if you isolate these cells and put them in culture, they can differentiate into lipid-filled cells, which you see on the right, which are stained with oil red O, this lipid dye. And so this really identified for the first time an adipogenic population of cells that reside within the skin. We showed that these cells proliferate, and they do form about 25% new mature adipocytes with each round of the hair follicle cycle. And in data that I won't show you, we also showed that if we inhibit this process of adipogenesis, we block the regrowth of the hair follicle cycle. We think that this effect resides within the immature adipocyte precursor population, and so we're actively investigating what could be the molecular mechanism by which immature adipocytes contribute to hair follicle cycling. What I'd like to spend the majority of the lecture on today is our work on wound healing and our unpublished data looking at different mesenchymal cells in wounds and how adipocytes might contribute to tissue regeneration. So we know that after an injury of skin tissue, there's a process of inflammation in which monocytes will migrate into the skin and form a macrophage population that stimulates the repair phase in which keratinocytes reseal the epidermis, fibroblasts proliferate and secrete extracellular matrix, and blood vessels regenerate. We have used mice in which we are able to label adipocytes specifically with membrane-bound GFP to follow their activity after injury. We use a model of punch biopsy from 4 to 6 millimeters in these experiments. We can also label adipocytes with an antibody against perilipin, which marks the lipid droplet within mature adipocytes. And so you can see that immediately after injury, the GFP-positive adipocytes also express perilipin, indicating they are mature adipocytes that contain a lipid droplet. However, if we look 16 hours after injury, we can see a population of adipocytes that lacks this perilipin-positive adipocyte marker, suggesting that they've lost their lipid droplet. So we wanted to test the hypothesis that adipocytes were undergoing a lipolytic process where they were breaking down the triglycerides and releasing them into wounds after injury. To do this, we crossed a mouse model that allowed us to delete the enzyme responsible for cleaving triglycerides and releasing fatty acids, ATGL, and we did it in a specific way where it's only deleted in the skin and only deleted in adipocytes. And so by inducing tamoxifen of this adiponectin CRE-ER mouse line that's crossed to the ATGL phloxed, what we found was that 16 hours after injury, these mice still retained their perilipin lipid droplet, unlike the control mice which lost this lipid droplet after injury. And if we look at lipid content within the wounds themselves by lipidomics, what we found was that these mice that are unable to release lipid display significant reductions in fatty acid levels within wounds. So this really says that adipocytes release fatty acids into wound beds, and this occurs immediately after injury. So of course we were interested in, and this is summarized here, so we think that adipocytes have a lipid droplet that they then, through an ATGL-dependent mechanism, release fatty acids and break down the triglyceride to provide lipid into wounds. And so we wanted to understand what is the mechanism, are these fatty acids functional within wound beds? So to test this, we then looked at the wounds of these mice after injury, and we initially looked 1.5 days after injury. In our model, this is the peak of inflammation when macrophages are present within the wound beds. And what we can see by flow cytometry is that the CD11B and F480 positive cells that are macrophages are significantly reduced within wound beds of these mice that cannot release lipid into the wound bed. And so this suggests that adipocyte lipolysis is required for sparking the inflammatory response. Consistent with this hypothesis, we see further defects in these mice if we look 5 days after injury during the repair phase. So we see that CD31 positive blood vessels are reduced within these wounds, and that's consistent with our experiments and others' experiments in which we deplete macrophages. We can see that these cells do not regenerate. And so our model is that after injury, adipocytes release lipid into wound beds, and that this results in the recruitment of monocytes to the wound site, and that this can then stimulate the repair phase that allows proper healing. In mice that lack adipocytes that can undergo lipolysis, or in other experiments that I didn't show you where we deplete dermal adipocytes specifically, we see a lack of the inflammatory response, and ultimately this leads to defects in the repair process, including defects in revascularization. We think that this is important because we know that obesity and diabetes can impact adipocytes in both what fatty acids they contain, as well as their ability to undergo lipolysis. And so we're actively investigating whether diabetic mice and humans have defects in lipid content within their wounds, and whether this could help as a treatment of chronic wounds that occur in diabetic patients. In addition to our analysis of wound healing, we've also noticed that this adipose layer within the dermis decreases in size with age in mice, and this is well known to happen in humans as well. And when we looked at the adipocyte precursor population, we found that it was also significantly reduced in aged mouse skin. And so we were curious as to, since aging affects wound healing, we were curious as to whether these immature adipocyte cells, adipogenic cells, could also regulate wound healing. And so we know that adipogenic cells and other mesenchymal cells during embryonic development derive from multiple sources of cells. They can come from the neural crest as well as other mesenchymal precursor cells. Several seminal studies in recent years have identified two populations of cells that can be marked and traced to the skin. And these markers, this DLK1 and engrailed 1 Cre, were thought to be marking the fibrotic and fibroblast line that could form myofibroblasts within wound beds. What these studies showed was that these cells marked, interestingly, with the same cell expression markers that we had previously found on the adipogenic population, including SCA1 and PDGF receptor alpha. And so we wanted to understand what is the relationship between the adipocyte precursor cells that we had identified and these other fibroblast populations. So we looked at this, we obtained the mice that were previously used to lineage trace these fibrotic cells, and what we found was that the GFP positive cells that were marked in those experiments also label the adipocyte precursor cells that are SCA1 positive and CD26 positive, and they specifically mark the CD34 or CD29 high population. And so we were surprised by this, and so we wanted to understand how this might change with wound healing, because that's where these experiments were shown to mark fibrotic cells. And so if we use this panel of CD34 and CD29 expression to analyze these cells, we identified sort of 4 populations of mesenchymal cells. Those that were adipocyte precursor cells are double positive, and we also noticed a CD29 high population and a CD29 low population. In a 5-day wound bed, when you see the majority of fibroblasts entering into the wound bed, we found that the adipocyte precursor cells were reduced in number in comparison, and that the CD29 high populations were elevated. When we looked at these populations further, we saw that these two populations of cells, the adipocyte precursor cells and the CD29 high positive cells, both express smooth methyl actin as well as CD90, a fibroblast marker. And so this suggests that there's a previously unidentified heterogeneity within the myofibroblast population within wound beds, with 2 populations of cells serving as myofibroblasts in the wound beds. To look at this further, we isolated these cell populations and performed global transcriptional profiling. And what we found was indeed the transcriptional profiles of these populations of cells were quite distinct if you look at principal component analysis, where the adipocyte precursor cells were quite different from the CD29 high cells, even though they seem to be both fibroblasts based on those markers. And if we look at gene expression analysis, we see that these 2 populations express different extracellular matrix molecules and receptors, suggesting they might be regulated differently. And in particular, we were interested in the expression of lysyl oxidase by the adipocyte precursor cells. This is the enzyme that cross-links collagen, and so we thought that this might reveal a functional difference between these 2 cell populations. And indeed, if we look at collagen production, we see similar levels between the two mesenchymal populations. However, the lysyl oxidase activity assay, when we isolate these cells and put them in culture, the adipocyte precursor cells can cross-link collagen to a greater degree than the CD29 high positive cells. So this really says there's a functional difference between these two populations within wound beds. And so in summary, thus far I've told you that we've identified a function of adipocytes to release lipid during inflammation, but we've also identified a population of adipogenic cells that become much more like a myofibroblast during the repair process. And there seems to be two myofibroblast populations that exist, this adipocyte precursor population as well as the CD29 high population. And so we wanted to understand how is this heterogeneity regulated? And we hypothesized that this might be due to the inflammatory response that immediately precedes the repair phase. We analyzed global gene expression, trying to understand how these adipogenic cells change in a wound situation to understand how they might be regulated differently to become a myofibroblast population. And interestingly, we identified several receptors on the adipocyte precursor cells that were receptors for ligands derived from monocytes and macrophages. So we hypothesized that macrophages might be contributing to fibroblast heterogeneity. To test this, we deleted the macrophages in mice that express MGL2. We had previously characterized these mice as being able to deplete the anti-inflammatory macrophages that come in late wound beds. And indeed, if we look at these mice, we find that the proliferation of the adipocyte precursor cells is significantly reduced in wound beds of mice lacking these macrophages, whereas the CD29 high and the double negative populations their proliferation remains similar. And so what this suggests is that the macrophages are able to specifically stimulate the proliferation of this adipogenic population, and that contributes to myofibroblast heterogeneity in the wound beds after injury. And so what I've described to you today is our work analyzing how different mesenchymal populations are regulated within wound beds. We believe that there's an unappreciated heterogeneity of mesenchymal cells within the wound bed, and that fibroblasts are not just a generic cell that we all think of them, but rather there's a heterogeneity that might lead to functional differences in both scarring and the function of skin after repair. We've also shown that adipocytes can regulate wound healing through the release of lipid, and that we are actively trying to understand what lipid is exactly being used to spark inflammation during this process. We think that the stroma is a rich source of new information for how we can treat skin diseases, and we're really excited about our future work in this area. I'd just like to close by thanking my laboratory. The work that I talked about today is primarily the work of a very talented postdoc, Brett Shook. He's on the job market next year, so please someone snatch him up before he goes. I'd also like to thank my funding from Yale as well as from the NIH, the Scleroderma Foundation, and the state of Connecticut, also my collaborators. And I just want to put a final word. So I decided this year that I'm going to run for state senate because I believe that our world needs the voices of all of us. If you care about your schools, you care about your roads, or you care about the funding of science, we really need you to speak up. We cannot stay within our ivory towers and our laboratories. We have to get out there and speak. I've been going to town halls for my senators and representatives, and I always ask about the NIH budget because even the public doesn't understand how we need more money. And so I think it's really upon us to get out there. The world really needs our voice. This is a picture of my two daughters where I was speaking in front of 3,000 people for the March for Science last year. So you can find out more about my campaign, and I appreciate so much the society, and thank you so much for the opportunity.